Hello everyone, my name is Armin. I'm working as an innovation fellow at Lancaster University. Here I'm working with the companies to analyze the industry problem, find the solutions, and to develop smart materials that improve the existing product. In this presentation, I'm going to talk about additive manufacturing technology, and my colleague Tom is going to show you our capabilities at Lancaster University. So, what is additive manufacturing? Additive manufacturing is a process of joining materials to create an object from computer-aided design, CAD software, or 3D object scanner, usually layer by layer, which is in contrast to traditional manufacturing that often requires machining or other techniques to remove excess material. There are a variety of different additive manufacturing processes such as powder bed fusion, binder jetting, vat polymerization, material extrusion, sheet lamination, directed energy deposition, and material jetting. Later, my colleague Tom is going to show you our equipment for each of these techniques. So, why would I use additive manufacturing? The most important one is to reduce prototyping costs. Modifying a design during a manufacturing in conventional manufacturing can lead to a substantial cost increase or time delays as tools on manufacturing lines are adjusted. Therefore, AM parts are commonly used during a pre-launch activities for a product testing and validating a design. Additive manufacturing solves this problem by moving away from this static design and allowing engineers to manufacture several iterations of a single design in a cost-effective way. Also, if manufacture requires only few of the same part, it is likely faster to print them. The biggest advantage to additive manufacturing are creating a complex geometries and optimized topology for lightweighting. The more complex object, the faster and cheaper it can be made through additive manufacturing in comparison to traditional manufacturing method. Functionally graded material, or in short FGMs, represent a class of novel material in which composition or macrostructure gradually change along various directions, resulting in a gradual change in properties and function which can be tailored for enhanced performance. Creating something like this is quite difficult, even with additive manufacturing, and sometimes is impossible to do with a conventional conventional manufacturing method. So, when you use additive manufacturing, there are some challenges. I think the most important one that you need to understand that is AM cannot replace a conventional manufacturing. A lot of SMEs who come to us normally ask us if they can replace a conventional manufacturing with additive manufacturing. And our answer is no. This is simply because traditional manufacturing is still faster and less expensive in long run. Printing out every unit will take longer time. However, complex geometry tailored to particular customer requirement, which may not be achievable with the traditional approaches, can be manufactured with a less material and lower overall cost. The second challenge is the size limitation. In most cases, the maximum available size for printing a polymer is about 1 to 1.5 meter in size, while for metals may only be around 3 to 400 millimeter. Although larger machines are available by using a robotic arm, they will come at a cost. The third challenge is printed objects require post-processing. Many parts that are additively manufactured need some post-processing to clean and smooth out the rough edges. This accounts for 30 to 60% of the overall production process. This is not a major problem when you use additive manufacturing for prototyping. However, as the technology is moving toward the end-to-end manufacturing process, the post-processing becomes the major barrier for having a AM production line. The fourth challenge I can mention is the quality consistency. Additive manufacturer faces a specific challenge to produce a reliable part with a consistent quality. especially in producing a fully dense metal part. For example, using the same print parameters can still lead to a difference in production of the same part. And finally, material availability. 3D printing technology can be used for a wide variety of materials, including metals, ceramic, polymers, and composite. However, there are also limitations, as only a relatively small range of material are suitable for such a procedure. So now I'm going to hand over to my colleague Tom Abram, Senior Engineer at Lancaster University, to show you our capabilities at Lancaster University.
Hello, I'm Tom Abram. I'm Senior Project Engineer with the Engineering Engagement team, who are primarily concerned with business engagement with the engineering department. So we deal a lot with SMEs, but also with large companies and multinationals. We've been here a long time, we're in our 19th year now, doing this sort of work. Now over those years we've built up quite an extensive range of additive manufacturing equipment. So this area is our FDM suite of machines, predominantly Ultimakers. So we've got Ultimaker 2 Pluses, Ultimaker 2 Plus Extended, we've got an Ultimaker 3 and a couple of Ultimaker 5s. Now they're the workhorses, that's what we generally tend to use more often than anything else. Simply because they're easy to use and they're cheap to run. So we do a lot of projects. We do a lot of projects with businesses, but we also do some undergraduate work. We do some work with academics and researchers and do our own research with them. So if we need to build anything larger, still using the same technology, we've acquired 2 machines from a manufacturer called Builder. So we've got the Extreme Pro 2000 here. So that will build up to, well, the build plate's 700 square, up to 1.7 meters tall. So this is obviously a turbine blade, and this is about half the maximum height that we can go to. Okay, so this is our Builder 1500. Very similar to the 2000, but a slightly different aspect ratio. So this has got a build bed of 1100 by 500 millimeters with a build height that's slightly shorter but 820 tall. We've also got our suite of reprocessing equipment. So we've got this set of equipment from a company called 3D Evo. So we've got the filament, the polymer shredder, to reprocess failed prints, support material, that sort of thing. Then we've got the pellet dryer to dry those pellets. Then we can feed them into this machine to extrude our own filament. So not just reprocessing of existing materials, but we can also start playing around with new materials, putting additives in, that sort of thing, to make our own specialist filament. Okay, so this section is our resin machines. So here we've got several machines from a company called Photocentric, who specialise in what's called DPP, so daylight polymer processing. So it takes a photoreactive resin, shines a light on it, where the light hits it, the resin hardens. We've got the large machine here, which is the Magna, that's got quite a large build volume, about 500 by 400 by 300 build volume. Then we've got a couple of smaller machines. We've got the HR2, that's probably about A5 size by about 200 or 300 tall. And then we've got a smaller machine that's around A6, but more precise. So if we want to do smaller but higher quality models, we can do on the LC Precision. We've also got a Form 2, and we're in the process of acquiring a couple of Form 3s as well. Okay, so this is our Stratasys J750, which is a polyjet machine. which again uses a UV curing resin and jets it out of it's ostensibly inkjet heads here, and there's 6 material heads and 2 support material heads. Sprays it onto this bed that's about 450 by 300 by 300. I can't remember the exact build area, but so what this will allow us to do is do full colour print, similar to your inkjet printer, where it blends the different coloured materials, but it'll build it up in layers so you get a full colour 3D print. It'll also allow us to mix different resins, so we've got an ABS mimic and various other ones, flexible mimics, and you can blend those to tailor the properties of whatever you're building infinitely effectively throughout the part. So you can go from a fully rigid material at one end to a fully flexible material at the other end, and blend that through the part, so every single node can have a different blend of materials. Almost impossible to do with any other process, certainly conventional. So we're in a different lab now, but this is our powder material processing area. So here we've got 2 metal 3D printers. So this one is Realizer 100, and this uses metal powders and a fibre laser to melt the powder together in individual layers, typically around 50 microns, to form a solid part that's almost 100% dense. The machine next to it is our newest acquisition. This is the Meltio 450. Now this uses a combination of wire extrusion and metal powder spraying. So we can have multi-material extrusion, so we can blend different materials together, and also spray various materials from a hopper with the air feed, the argon feed. Okay, so this is the 3D Systems S Pro 60. Now this processes polymer powders, typically nylon 11, nylon 12, but there's also flexible powders. There's investment casting powders that you can put in. You can put glass fill powders and various other things. Spreads a layer of powder, uses a CO2 laser to sinter that powder together. And this exactly the same process, but on a smaller scale, is the Lisa by a company called Sinterit. We're in the process of getting 2 of the latest iterations of the Lisas. Does the same job as that, but because it's smaller, it's easier to turn the machine around, to reprocess the powders, to sieve them and everything else, unload the machine, but obviously not as big a build volume, not as powerful a laser. The last machine is the Solidscape Z Studio in the corner. Now that's quite a specialist machine. That will only print in wax, and it's specifically designed for investment casting. Very, very precise. It's by far our most accurate machine and most precise machine, with layers going down to around 6 microns.
Thanks for that, Tom. So now I'm going to give you a little bit more information about how Lancaster University can help you. With the GISMO project, we can help you to investigate the additive manufacturing technique for the first time, establish your own in-house capabilities, prove a new concept design, product or process, overcome a problematic design or material issues, increase your existing materials palette or capabilities and capacity, and understand the latest thinking and techniques. If you want any more information or you want to discuss your ideas with us, please get in touch. Thank you so much.